Welcome, everyone. Namaste.
Namaste.
We've got lots of folks here who've joined us this morning. Being that it's a few minutes after the appointed time, I'm going to go ahead and get started. So today we'll be talking about visualizing circular functions using Desmos. This is the second, this is part two of a two-part series on connecting trigonometry to its geometric roots. But I want to take my hat off to Amrit Thapa, who was instrumental in planning the breakout sessions and did much of the preparation for this particular session. Today's program, we're going to do some geometry review of some vocab, angle, central angle, major arc, minor arc. And then the first breakout session will be to do deep observation, to study a figure and see what it is you can see. Then we're going to have two Desmos breakout sessions. So the first breakout session will be a little bit shorter than the other two. The second and third breakout sessions will involve Desmos. The first Desmos session will look at the unit circle and something called a wrapping function in radian measure. And then we'll discuss the idea of arc length and length preserving transformations. We're going to be doing wrapping in unwrapping today. So vocabulary, a circle is a set of points in the plane equidistant from a fixed point. The fixed point that the other points in the plane are equidistant from is called the center of the circle, and the fixed distance is called the radius. The word radius is used in two ways. It's used both to talk about the length or distance from the center to the circle, and it's also used to talk about a segment that connects the center with the point on the circle. So there's the territory inside the circle, and there's the territory outside the circle. So just as a line divides a plane into two half planes, a circle divides a plane into the interior and the exterior. The circle is actually just these red points. And so when we talk about the area of a circle, we really mean the area of the interior of the circle. A circle has length. It's just a curved line. If you think for a second, a line, if you put one point on a line, it would divide the line into two pieces. But as you can see, when we put a point on the circle, it just creates a giant arc. Okay. If we have a line pass through a circle like a secant line, it divides, you create a minor arc and a major arc. The last time we looked at the unit circle and various segments associated with an angle. So here alpha would be a central angle. And so that creates an arc. We didn't focus so much on that arc last time. We focused on these segments, sine, cosine, tangent. Now we do have the radius here, and in the unit circle, the radius is 1. Cotangent. So all of the 6 trig functions can be seen as segments associated with these. So we might call these circular functions because not only are they associated with triangles, they're associated with circles. So a circular function and a trigonometric function, one and the same thing. Tangent is a circular function. Tangent is a trig function. Tangent can be seen as a number or a length, just like we can think of the radius of a circle as a number or a length. And we can also think of the tangent as the segment itself, just like we think of the radius. So any of the 6 trig functions can be seen as line segments, just like we can think of the radius as a line segment. And so this was the focus of our last webinar, to to see the trig functions as line segments. And we are using GeoGebra. Today we'll focus more on Desmos. Now, this circular approach to trigonometry actually has deep historical roots. And the relationship between angles and arcs also has deep historical roots. Okay, I'm going to open all rooms. And please join your breakout room. Welcome back, everyone. In the breakout session, you should have been studying this figure, and hopefully you had a chance to discuss some of these questions. So I'm wondering if someone can report, let's see, some ideas to consider for discussion. Starting from this bottom point, talk about arc length, major arc, minor arc, and in British English, we say anti-clockwise. In American English, it's counterclockwise. So we're talking about like starting at this point on the circle and making your way around the circle. So can someone share their findings of a breakout group?
Can I say, sir?
Yes, please.
We discussed that if we go counterclockwise, and I think this is C, G, then up there is C, we get one minor arc. If this is minor arc, the big one, the other side is the major arc.
So the major arc would be this whole other distance around.
Is major arc. And there are right now inside the circle 5 diameters, and the central angle made by GC is this center is O, sir, or C? What is this, sir? Center?
I don't know. I can't read Arabic, okay, or whatever this is very well.
So the arc starting from G to C, first arc, and the arc equal to this is on the other side. It looks like AB.
Right. So if you have a diameter, if you have 2 diameters, then you have vertical angles and you have equal arcs. Very cool.
Yes. And we guessed that the arc which could be equal to the radius is either GM or AL.
Okay. So the main ideas we're trying to get across is that you have circles and you have arcs. The other thing is that associated with each arc on the circle is an angle. And one of the things that we want to discuss in this next session is L equal to R times theta. And that this actually works best when you use radian measure. And so to try to get some sense of radian measure, we're going to actually do a Desmos activity. And so somebody in your group is probably going to go into, all you have to do is type desmos.com in a browser and then open up the graphing calculator. And you can do things like, if you wanted to create a circle, you could say x squared plus y raised to the second power. So you have to use the caret. And then once you're up in the superscript, you have to use a right arrow to get back to the main line. And if we wanted a unit circle, we would make this 1. You could make this, I guess, r squared or something. If I said r raised to the second power, then I'd get a slider, and I have the unit circle, but I could make the circle bigger or smaller. If we look at a 90-degree angle here, for instance, the first quadrant angle, there's an arc associated with that, a minor arc, and then there's a major arc. The degree is 90 degrees, and the other direction is 270 degrees. But how many radiuses is that? So if we look at the radius of the circle, how many radiuses is this angle is this arc. The 90-degree angle looks like it's more than one radius of the circle, regardless of how big the radius is. But things are simplest when we use a radius of 1. So in the second breakout, you're going to get a chance to play around with Desmos and to investigate the relationship between a circular arc and a straight segment. So before we go to breakouts, I brought in some props here I wanted to show you. Can you see me okay? I've got a round cup and I've got something, and I can take a straight segment and I can wrap that straight segment around a round cup. And so we're going to do this mathematically. We're going to wrap a straight line around a circle. And so wrapping and unwrapping. So you want to have, you want to preserve length. You can bend something and it doesn't change its length. So we're going to be working with lines, not with bungee cords. Bungee cords, bungee cords can change length. We're going to work with segments that preserve the length even when they're curved. You know, there are things you can measure with that are straight, but they're hard to bend. We want to use an object like a string or something like that, that preserves length, but it can be bent, can be wrapped around a circle. So we're going to be doing wrapping and unwrapping, but we are going to preserve the length. The length will not change when we wrap. The length will remain the same, but the shape will change. The length will not. So let's go into the second breakout sessions and investigate this using Desmos, which is a very useful tool for investigating wrapping and unwrapping of segments. Breakout room. I'm going to go ahead and do this in Desmos. I'm going to create cosine t, comma, sine t. So if I do that, that's kind of cool, but it can be even groovier if I make this max value b, and then I can see the circle being created for different values of b. So John, is this making any sense what I'm doing here?
Yes, very much.
Okay. And then, so this is the same as the equations x equals cosine t, y equals sine t. I'm wondering if I could actually put in x, comma, y and make it look like that. It doesn't like that.
No.
So, but that's essentially what it's doing. Okay. It's looking at it as a vector valued function of one variable. So the input is t, the output has two components to it. It has an x component and a y component. And then we can cleverly say, what about 1 comma t, and use b as the maximum value for that. So this slider will control both the red graph and the green graph. And so this is the wrapping function idea, that here, when b is 2, this red length is 2, and this green length is also 2. It's just been, the straight line segment has been like a string wrapped around the unit circle. And so that's what they're exploring in the breakout room. Let's see, do they get any farther than that in the first one? They create a little table, it looks like, so that there's endpoints for the, and so we can use the table feature in Desmos. The endpoint here would have a b value. The maximum would be cosine of b, sine of b, and here it would be, I guess, 1 and b. And so you get an endpoint for each of those, and that just makes it show up a little bit more strongly. So this would be x component cosine of b, and the y component would be sine of b. Oops, it's supposed to be on the
Whoops.
other side
Yeah.
of the line.
Yes.
Teacher technique.
I do like adding
now
that.
you can see you can see this, and let me drag this down so I can, as I move B to be larger, I can still see it on the screen. Okay, that's better. Now
Yes.
I can go all the way out to about 6.28. And so now if I wanted to, I could put in another little table. And let me do that. I'm going to add a table. I'm going to have 1B, or actually, I'm going to go 1, 0. And then I'm going to go to the origin, 0, 0. I'm going to try to create a central angle. And then I'm going to go to the point on the unit circle, which would be cosine of B, sine of B.
Okay.
And then if I press on this dot and hold it, it will let me draw lines connecting the points in the table.
Yes.
And then that will make it look like an angle. So as I move B, I've got this central angle of the circle, right?
That's very cool.
And so here we have a graph of the unit circle. And then we have a graph that goes from the point 1, 0 around to the point cosine of t, sine of t. And this arc here is actually controlled by a slider. Right now, the value b is 1.3. So the distance from 1, 0 to this point cosine of b, sine of b on the unit circle, this length is 1.3. We've also created a line segment that goes from 1, 0 up to the point 1, b. So this red vertical segment is length b. Currently it's 1.3, but we could stretch it out to be, say, 2 units long. Now the red segment is exactly 2 units long, and it corresponds exactly to this arc of the unit circle, which is 2 units long. And the radian measure of this central angle, therefore, is 2 units because it is 2 radiuses. If we look at this green central angle, one radius is 1 unit long, the other radius is 1 unit long. This this distance of 1 plus 1 is the same 2 units as the arc. We've got this red length 2 that has been wrapped into the curved arc length in black, which is also exactly 2 units long. So this is 2 radiuses of arc length, and so the angle is a 2 radian measure angle. And so these tables allow us to graph points. So the point 1, b, which is up here, is graphed because of this table. It's in black because this color is black. And the point on the unit circle, cosine b, sine b, which particular coordinates we can get by clicking on that point. That's the cosine of b, sine of b. In fact, that's the cosine of 2 radians, comma, the sine of 2 radians. And then we have, because we've graphed the unit circle, we actually have in light blue the full unit circle. And then the last thing we have is just in order to graph this central angle, we're going from 1, 0, the first point, first ordered pair in the table, to 0, 0, the origin. And then we go to the point on the unit circle, cosine of B, sine of B. And then we connect those. You can see it shows that the dots are being connected. So this is really just a line plot from one point to another point to another point, and it forms a central angle there. So in the breakout sessions, the discussions are, what do cosine of t, sine of t represent? What does this expression, why does this create a vertical line? Why do the arc length and the vertical length change together? Why does this length change with this length? So we observed some things, but now we're asking some why questions. Okay, so the first question is, what do cosine of t, or you might say cos t, and sine t represent on the unit circle?
Mm-hmm.
Yes, so I'm looking for a verbal response to that question.
Was the order pair that represent the order pair?
If you put these together, you
Oh
could
yeah,
create an ordered pair.
if you put the together, T is angle, that is angle at the center, T.
Yes,
That
and
is in
what unit of measure are we using?
that is in radian.
Yes, sir. So T is in radian measure. So the central angle of T. So T is the central angle. T is also this arc length. And so if you put these together, you get an ordered pair. So which part of the ordered pair is cosine of T? Is that the X or the Y component?
Yeah, cos is X component and sine is Y component.
Okay, so in this particular picture, it looks like cos T, the cosine of T, is really tiny, right? The X component, it's just barely greater than 0. The Y component is nearly 1. So the cosine of T would be nearly 1 unit. And if we had a live Desmos, we could actually go to that same location that we were at by moving the slider here. So it looks like maybe B, the radian measure, the arc length is about 1.5, and then the X component of the point on the unit circle is cos T, and the Y component is sine T, and cos is a small number, just a little bit bigger than 0, and sine of T is almost 1. And if we click on this point, we'll see approximate values. So the cos of T when we have 1.5 radians is merely 0.071, less than a tenth of a unit, whereas the sine of T is nearly 1, it's 0.997. And if you look visually, you can see if this is 0.5, each of these thin marks is 1/10. So yeah, it looks like we're less than a tenth of a unit to the right of the y-axis, and we're almost up to this line, y equals 1 in the y component. So we can get kind of a numerical, visual, a length perception of what the relationships are between the angle in radians and the sine and cosine values, which are just points on the unit circle. Okay, beautiful. I'm wondering if someone else would be willing to explain why the expression 1 comma t, why does that create a vertical line segment? So the 1 comma t expression here which in this picture is shown in orange color. It says B is equal to 1.5, and it looks like this length is 1.5 vertically, right? Because 1.5 is here. It looks like it's a portion of the line x equals 1. Why would this expression 1 comma t create a line segment like this? Would someone other than Vinod be willing to share? Anil or Kabita or Suraj or Tapan or Tika? Would you be willing to unmute your microphone and share your thoughts? Suraj, please.
Yes, thank you, sir. It gives straight line as x component is constant, sir, 1 unit.
Ah,
And
the x component is a constant of 1. I gotcha.
yes.
Okay.
And y component we can just change its variable so that we get straight line.
Yes, and let's look underneath this expression 1 comma t, if you would please. It says t takes on all values between 0 and b. So when t is 0, we have 1 comma 0, which is this base point, if you will, the lower endpoint of the segment. And then as the upper maximum value changes, this would change the length. So let's go into the live Desmos. When I change the value of b, this x equals 1, y ranges from 0 to the value of b, which in this case is 0.6. So we have all possible y values from 0 to 0.6. But x value, as you said, remains constant because it has no variable in it, just the number 1. So we own for every single point on the red curve, x is 1, and it's not really a curved curve because we have one of the components constant. Whereas on the other parametric expression, both the x and the y components change as the t maximum is increased. So the b value slider is providing the maximum value for a band of t values, t ranging from 0 to b. So we get, these are really equivalent to parametric equations. I think we've got people coming back. How much longer till everybody gets back, Deependra?
I think all they are back.
Okay. The picture I have, you were looking at a picture something like this in your breakout groups. I've added a few additional features to this. In your breakout groups, you had an expression cosine of t, sine of t. This is almost like a vector pencil. If you think of the base of the vector being at the origin and that it points to cosine of t, sine of t for values from 0 to b, it would be like a pencil drawing this curved line here for t values between 0 and a b of 1.5. So from 0 to 1.5, we're getting all of the points on the unit circle that have radian measured from 0 through a radian measure of 1.5. Meanwhile, simultaneously, we're graphing x equals 1 and y equal t, where those t values range from 0 to b, with b having a particular value of 1.5 in this freeze frame snapshot. In my live Desmos, I put in the unit circle in light blue, just as a reference. I've also put in the central angle in green. So going from the point 1, 0, using this last table, starting point 1, 0, then going to 0, 0, the origin, and then going from the origin which out to cosine B, sine B, which is a point on the unit circle. This table, together with connecting the dots going into here and turning the connecting line segments on, it's going from the first point to the second point to the third point, or from the first line of the table as an ordered pair to the second line of the table as an ordered pair to the third line of the table as an ordered pair to create this central angle. So as B moves, that central angle changes. And I think in your group, you use the table feature to create dots for the points 1B, which is this location right here, and cosine of B, sine B, which is the point on the unit circle. So when B moves, it controls 1, 2, 3, controls this, one thing, two things, both of these tables. So this parametric expression and this parametric expression, the maximum value is B. And in these tables, we have points which contain B as a variable. So 4 things change when we move the slider in this particular configuration. One of the things that changes is this circular arc. Another thing is this line segment. And then, because of this, the black dots here and here change. And this black dot is overwritten by a green dot in the next table of the central angle. So the central angle changes, the associated arc. Now, if we make the central angle big enough, we have a reflex angle, right? An angle greater than 180 degrees. And we have so instead of thinking of this as the angle measure is this larger angle measure. And we can see that because the black arc has this, the black arc is, I guess, being drawn using cosine of t, sine of t. And the value in radians of B is 4.5. So the red segment, let me make this a little bit different. This red segment is 4.5 units long. The red segment is wrapped around the unit circle and changes its color to black. And this also is 4.5 units long in a curvilinear way. And it's associated with this central angle, and it's the major arc of this angle.
Not 5.4, not 4.5, I think.
It's 5.4. Thank you. I'm glad someone's listening. So 4.5 would be smaller. It would be over here. If I could learn to read, I'd be all set. So eventually, I guess I'm dyslexic. I'm reading it backwards. Thank you for that correction. So it's 4.5 now. Before it was 5.4. And so this is, whatever it is, it's the radian measure. It's the arc length. It's the measure of the central angle in radians. So the arc, the angle, the radian measure, the arc length are all one and the same thing. And I think it helps students to conceptualize this, to see this red as being wrapped. And in the United States, we talk about a wrapping function, that we have this geometric transformation of the red vertical line into the black arc. Okay. Anything else that came out in your discussions in your groups that I have not touched on so far? Did anybody get to what is 270 degrees in radians? And what is 1 radian in degrees?
कसैले आफ्नो एन्सर भोलुन्टियर गर्न चाहनुहुन्छ प्लिज?
Yes,
It is 10 to 60 degrees.
87 point something degree, 1 radian equals to.
गोपालजी?
1 radian almost 55. 57 point something. 1, 2 or something.
57.3.
Let's see if Desmos can help us out here. What if I said, let's see, 1 radian times, what would it be? 180 degrees divided by pi. Maybe I could just type pi. Oh, look at that. Isn't that 1 radian, if I convert it into degrees, would be about 57.3 degrees. Does that make sense to everybody? So in addition to all the graphing capability that you have in Desmos, if you want to do a simple computation like you would on a calculator, you can just type that in the algebraic panel on the left, and it will give you a number. How cool is that?
Pretty much.
I like it a lot. Now, what about the other question? We are trying to take 270 and we want to multiply that. And I guess it would be in reverse now, right? We would say pi divided by 180. And so that would be about 4.71. So I'm at right now a B value of 1. And so this central angle is 57.3 degrees here. And if I try to go to 270 by moving B,
4.72B.
I can't get there. I can get to 4.7 or 4.8, but even if I can't get to 4.71238889, I'm not going to have that much accuracy. I could rewrite this and use fractions of pi for my B value. I could click in here and say, I want to go, say, from 0 to 2 times pi. And I want to go in steps of, let's say, pi divided by 24 or something like that. And then it would let me get to this number. Look at that. Do these look at all alike? 47123889803. It's even giving me more accuracy up here on my slider for pi over 3 radians. So this is the number pi over, or excuse me, please correct me. I'm having trouble getting my numbers mixed up. I said 4.5 and 5.4. How would I say this using pi's and fractions? Let's see, if I simplified this, what would that be? Oh my gosh. I may have to write it because my mouth isn't working right. So maybe I can get my pen to work for me. 270 degrees times pi over 180 degrees. The degrees would drop out, wouldn't they? And I could write this as 3 times pi divided by 2. So that is the length of this black arc, and that's also the length of this segment, because B is that value, right? So it's also this guy here. And it's also this guy down here. Okay? So numerically, it's our B value. Numerically, it's the same as 270 times pi over 180. And as far as a length is concerned, it's both the straight black vertical segment and the circular arc that goes from 0 to 3 pi over 2, or the 270 degree position, if you will. Wow, lots of connections there. It's probably
Very good
time for
connection,
another
sir.
breakout group.
Yeah. Vertical line is equal to the central angle in
So,
radian.
the central angle in radian. So if you want another connection, let's see. What happened to my pencil?
Excuse me.
Maybe I use this one. So what you're
Hello.
saying is that this central angle here, come on,
Hello.
draw.
It's me, Kailas. This red line, straight line, is converted to circle, means, and the circle circumference is associated to pi, means irrational number. That means this length segment is also an irrational quantity, I think. Can we connect in that way also?
Okay, I did not understand everything you said, Kailash. Can you repeat that slowly for me? I didn't. There's something I missed there.
Oh, sorry. This red line.
Yes, sir.
In the screen. And this is the circumference of the circle.
It is not. It is it's 3/4 of the circumference.
Yes, for the time being, but this segment represents the circumference.
This segment represents the arc length, not the entire circumference, just the black arc length.
Arc length. And arc length is in pi, irrational quantity. So this segment is also the irrational quantity, isn't it?
The arc length can be in pi, but it doesn't need to be in pi. There's no reason why the arc length can't be 2 or 3 or 1.5. So it's only in pi if you want to match up with degrees. If you have a nice round number of degrees like 270, then the arc length will involve pi. But 2 units of arc is a perfectly good amount of arc. And so when we had, so we tend to teach our students as if arcs are always fractions of pi, but that's only if we want to have a nice degree measure for the arc. So we're really kind of in the traditional curriculum where we're not allowing graphical representations, or we don't regularly use those. So here, let me close this out and make this something that would be more natural, like a max of, say, 8, and then we do a step size of, say, 0.1, then we don't have fractions of pi anymore. And we can't get the exact circumference. The circumference of this circle would be 6.28, and we can get 6.1, 6.2, or 6.3, or 6.4, something like that. But we're not going to get the exact multiple of pi if we use natural decimal steps. So this is actually not the entire circumference unless we make the value of b to be 2 pi. It's going to be whatever the arc length is, and it changes simultaneously. And so we're really wrapping the red line to create arc, which is part of the circumference. It's a fraction of the circumference.
Greg,
Yes, sir.
Thank you.
on the arc, is it possible to change its thickness slightly? Would that make any difference in the?
It might be, but not by me. I'm too klutzy.
No.
I don't know how to do that, John. I messed around with it the last couple of days. So what I've tried to do is just change colors, use black over blue and things like that to let it show up. That's the best I can do.
Well, that looks great.
Nice. Okay. Any other questions or comments? So that was, I'm glad you brought that up about this line is related to the circumference, but it's only a fraction of it. And this word circumference, I think, is overused. The circle is a set of points. Its measure, its length is called the circumference. Circumference is just a fancy word for the length of a circle, or so a circle has a length. It's how far around the circle is. But a lot of people tend to think of the circle as the circle together with its interior, but the circle is just this curved line, and the arcs are fractions of the circle. And so if we want to talk about the arc length, the length of the arc is a number, and that's a fraction of the circumference. So the circumference is a number, and the arc length is a number, and then the circle is a set of points, and the arc itself is a set of points. And we're actually physically transforming this vertical segment and bending it or wrapping it just like we would wrap a string. So this idea of taking something straight, taking a straight object and bending it around a curve, that's really what we're doing. And so we may only have part of the whole circumference of the cup, and we're just going to be looking at an arc length along that circle instead of looking at the entire rim of the cup. So the rim of the cup is a circle. It can be a circle. The circle is just the length here. Okay, well, it's probably time for the next breakout room because we're going to be running out of minutes otherwise. And the next breakout is in your instruction sheet is breakout session 3. And we'll be looking at the graph of the sine function. For those of you who are in the main room, do you want to have a discussion?
Sure, Dr.
The main room. Welcome back, colleagues. Sriram and Tapanji, we're looking at the configuration that you see in figure 12 in front of you. There's a green vertical line. There's a blue arc of a circle that is exactly the same length as that. At the end point of the arc of the circle is a point on the unit circle. The coordinates there of that point would be cosine t, sine t, and in particular, this purple segment is a directed line segment. You could almost think of it as a vector going from the x-axis to the unit circle, and then we translate that vector over here, and we have a downward pointing vector of exactly the same length. So the coordinate, the y coordinate here is sine of t, the y coordinate here is sine of t, and we've simply translated it. The distance from the origin to this red dot is actually the arc length on the unit circle. That arc length is t or theta, and this distance, this green distance, is also t or theta. And so this vertical distance is then wrapped into a circle, and then that circular arc is unwrapped and straightened back out so that this green vertical line and the black axis from zero, from the origin over to this red dot, that's the same length t. So this distance is t, and this downward pointing vector is sine of t. And so this graph of the sinusoid is actually created by unwrapping the unit circle and translating the y coordinate here. So first we wrap the green to the blue, then we unwrap the blue and straighten it out along the x-axis and simultaneously translate this segment over here. And that's how you can physically create the sine graph. Pretty cool.
Dr. Foley, all our friends are back into the main session.
They are. Welcome back, everyone. I was just chatting with the folks who had been bounced out and came back. I'm going to try to speak slowly and clearly.
Not
I
as
get
a-
excited about this stuff and I start talking too fast. And it's hard to understand what I'm saying when I talk too fast. So I'm going to try to talk in a more deliberate, slower manner. I'm going to activate my Desmos. And let's take a look here. I'm going to come up here and I'm just going to limit the n values. I'm going to go from 0 to 2 pi. And I'm going to try to get so we can see almost everything here. All right. So I have a slider for B. B is driving the bus. All the pictures, all the various elements of this configuration are all passengers on the bus. B is driving the bus. B controls everything. When I move B, it lengthens this vertical segment. When I move B, it moves this point on the unit circle. It extends the arc around the unit circle. It moves this vertical segment, which is just tracking along. We're sort of dropping a perpendicular from the unit circle to the x-axis. So it's another passenger on the bus. And I'm the tour guide. So we're going on a tour of Sinusoid Land, which is a country in Antarctica. There is no such thing as Sinusoid Land. It's just part of Math Magic Land. So we've got lots of geometry going on here. And the dynamic nature that we can move this, B is the maximum value of this parametric representation, which creates an arc on the unit circle, because cosine of t, sine of t will always be a point on the unit circle. That ordered pair will always be a point on the unit circle. This is merely to create some points for us to see. This is actually creating the central angle. So when B moves, we can see the central angle in green. The central angle has a degree measure, but we really don't care about the degree measure so much today. We want to focus on the radian measure. How many radiuses is the arc? Well, that would be this black line, and right now it's about 2.4 radiuses. That's kind of hard for us to, all these decimals kind of get in the way. So I'm going to just change this maximum to 6, and I'm going to change this to 0.01. So we can move and lengthen the green. The green then wraps and becomes the black. And then over here, this point is controlled by our third parametric representation. We have here, I'm just going to write this if I can. I'm going to turn on a annotation. If I broke this down by components, this would say that x equals t, and y, the y coordinate, the y component, is sine of t. For those of you who've studied parametric representations, parametric equations, sometimes we talk about eliminating the parameter. and we would take these two equations and combine them into a single equation. If we notice that x equals t, we, by the reflexive symmetric transitive, I guess it would be the symmetric law, then t is also equal to x. And if t is equal to x, let's just substitute that equal value in here into the second equation and say y equals the sine of x. And so this actually plots out a graph of y equals the sine of x, which would look, whoops, if I wasn't so klutzy, it would look something like this. It should come out here at about 2 pi. It should have a minimum at 3 pi over 2. Here it should be just a little bit to the right of 1. And so if we extend this, let me see, it should create a graph here that would follow the sine curve. And if we wanted to go farther out, we could just change this maximum to, say, 8 or something. And then that would allow us to graph more of the sine curve. We could even graph it for negative values, but we don't have the geometry set up to see all the relationships for negative values. B is the length of this vertical segment. B is the length of this arc. B is the radian measure of the central angle. And B is also this distance. Let me try to turn my annotation back on and erase some of these other things that I've drawn earlier and try to share this. So B is this length. B is this length. B is the radian measure of this arc. And B is also the distance along the x-axis from 0 to the base of this point on the sine function, because the coordinates here are B sine of B. In general, any point on the sine graph would be T sine of T, but B, remember, is the maximum value for T. And so the maximum value for T is the outmost point on the vertical line, the outermost point from where we start, the end point, if you will, on the arc, and it's also the outermost distance that we extend the sine graph. When we come back and we move B, we can, of course, we can make that go farther. And now B would be the longer length, the longer arc, the greater distance along the x-axis. So the problem with freezing it and showing any one particular value is you lose the dynamic aspect of this, which is so powerful. So not only do we help students to visualize, but through the motion and the dynamic nature of this visualization, they can see the relationships perhaps in a deeper way than would be possible on a chalkboard or a dry erase board. So it's pretty the use of free tools such as GeoGebra and Desmos allow for students to visualize and conceptualize in a far greater way than would be possible otherwise. Now, it's my understanding that it is not common practice to graph sinusoids in secondary schools in Nepal. In the United States, all high school students who go, on to pre-calculus and calculus, that they will spend some time learning how to graph sine and cosine graphs and tangent and cotangent graphs and so on and so forth. So this is part of the normal curriculum for us. it really sets you up for calculus. In calculus, you do things like the following. The limit of theta tending towards 0 of the ratio of sine of theta to theta is, put it in chat what the answer is to this limit. What is the value of this limit?
1.
1.
How do you know? Explain it using this
By-
picture that we've created. Explain it using the picture that we've created.
I request sirs, each of you to write your answer in the chat box so that like each of us will have chance to think of the answer.
That's beautiful. So explain, and with your own Desmos, you can play with this. Where is theta? Where's the sine of theta? How do you know that this limit is 1? Use the chat, think about this, and then we can go from there. So this is actually a geometric fact. And it's the basis of all the calculus of all of the trigonometric functions. Without this geometric fact, you cannot understand the analysis of trig functions, the calculus of trig functions in a deep way. It's an absolutely essential understanding. So that alone, I think, is a sufficient argument that every high school student who studies math, especially in grades 11 and 12, should have the opportunity to graph sinusoids and to do this kind of work that we've been doing today. Our time, I guess we've been going for 2 hours, haven't we? I've lost track of time. So we've gone not more than 90 minutes. I apologize.
It's already more than 120 minutes, Dr. Fale.
It's after 7 in Nepal. Okay.
But it seems that the interest remains.
So I think I'm this 9 hour and 45 minute time difference has got me buffaloed a little bit. I'm going to zoom in if I can. And let's see, maybe I can do something like this. So where is the sine of t? I guess this vertical distance is the sine of t.
Mm-hmm.
And t is this. So if I were to annotate this is the sine of theta. This dotted vertical segment is the sine of theta. And the arc distance, the arc length, that is theta. So sine of theta is smaller than theta itself. So I'm going to turn off my annotation and I'm going to pull back here for small values of theta. The sine of theta and theta. The other place where we see theta in this graph is theta is this distance. This is also theta if we're on the sine graph. And we can see at this point that that theta is a little bit bigger than the sine of theta. It's probably easier to see here than to see here. But as we make theta tinier, this red vertical line is theta. So I'm going to erase some of this stuff because there's too much stuff on my screen right now. And I've moved things so that it no longer is all valid. The red line is t, and t and theta are one and the same. So let me get my drawing tool out. Here's theta, the red line. Here is the sine of theta, the dotted purple line. I'm just going to try to squeeze that in there. Sine of theta. They are virtually equal. And as theta approaches 0, they get even closer together. So I'm going to make this maximum here. Since we're only interested in small values, let's make the maximum, say, 0.5. That will allow me to have a little bit greater control as I move in. Theta and sine of theta are almost the same. Theta is the arc length or the straight vertical tangent value that we have shown in red, and theta, sine of theta is the purple. So if two numbers are equal, when you divide them, the quotient will be 1. And the closer we get to 0, the closer and closer that sine of theta and theta itself get to be the same. Now, theta and sine of theta are actually these tiny little distances, these little vertical heights right here. And they're almost the same. They're so close together, they're lying on top of one another on the screen, and you can hardly distinguish them. They're virtually equal. So what we're really saying here is as theta goes to 0, the sine of theta its value approaches theta itself. That only makes sense if you're talking in radians and talking in arc lengths and you think of theta as an arc. It doesn't make sense if you use degrees. So it's absolutely essential that students understand the circular approach to trig functions, that they understand radian measure, that they understand that in radian measure, the arc length and the angle measure are one and the same thing, because we know from that formula that we studied today that the length of an arc is r times theta, but if r is equal to 1, then that simplifies down to the length of arc and theta are one and the same. And in our setup, the number t is both the arc length and it's the angle in radians. So the big takeaway here, I think, is to think of trig functions in terms of their input being real numbers, and those real numbers can either be the arc length or the angle in radians. And that allows you to set yourself up to understand the calculus of trig functions. Without this approach, this is just a fact that students memorize and they have no conceptual understanding to ground it. Well, that's pretty much what I had in mind for today. I hope that you will forgive me for spending too much time, taking up too much time today to look at these ideas. And maybe we can get back together sometime in the future.
Dr. Foley, do you have any final words to say?
Namaste.
Namaste. Binod sir, do you have any final words to say? Because all you know that like this, these workshops have been jointly organized by Outreach for Outcomes at Ohio University and Department of STEM Education at Kathmandu University. So, Binod sir, do you have anything to say?
Devendra sir, thank you so much. Thank you so much
Yes, sir. Yes.
for all, especially Dr. Foley and the team from the US. Thank you so much.
Yeah,
I have something to say.
Sure.
Very short. This is a privilege that we have Dr. Foley. His time, his love for Nepal. That is what privilege we have had, and we will have this for the days to come. So thank you, Dr. Foley, Johnny, for joining us. He has always been with us, and it's a pleasure to be working with him in workshops for US teachers as well. So thank you so much for your love for Nepal, and thank you all the participants for being so excited and participating actively. Thank you.
Yeah, and then though Marian is not here today, like thanks to her as well, like she had been doing, like making a lot of efforts to support Nepali teachers since 2012. So thanks to her and thanks to all breakout leaders and the co-instructors.
And thank you very much to the participants.
Yeah.
Thank you very much. Was just mentioned, that level of active participation and engagement is wonderful and is greatly appreciated. And I hope that you have learned a lot, and that you can take Desmos and GeoGebra and some of the ideas that we've shared over the summer and bring those to your students and enrich their lives.